Want to start? Okay, so let's get started. Few announcements before we get started. One is we gave out problem set 1. It has a lablet and a written homework, so make sure you complete both parts. If you have any questions about anything, ask us on Piazza. We are happy to help you. Okay. The other thing is after today's class, you would have the basic information you need to do the first lab. Okay, so I'm just going to hand that out today a couple days early. It's due at the end of the month, so you still have plenty of time to work on it. Make sure you finish the lablet first, because it has some sample code that you could potentially benefit from when doing the lab. Okay, so do them in that sequence, but just to give you a couple extra days, I'm just going to hand that out early. I still due at the same time and end of the. Okay, so those two things you want to keep in mind. I did want to make one more announcement, and actually had a question about it. Next Thursday's class, we normally have Monday and Wednesday. Okay, next Thursday is a virtual Monday. The university is following Monday schedule, so we actually have 3 classes next week. Okay, it just so happens that I had some travel that I had planned some time back for going for a research meeting, so I'm not there on Thursday. So even though we have a class on Thursday, I am thinking I will either cancel it or have a guest lecture. But to make up for that class, I would like to schedule a makeup class. Okay, so I was thinking I will try to do this Friday, same time from 2:30 to 3:45, same time as the class time. So it will be on Friday. My question is, can some of you come to that slot? Not required that everybody come, but if some of you can come, I don't want to teach an empty class to record it and give it, but if at least some subset of you come, there will be some Q&A. Okay, is that fine? Is that some of you able to come, even though not everybody can come, and then the rest of the class can of course be recorded and handed out. Okay, if that's okay, I will send out an announcement after class. I still have to book a room. Okay, because I need to know where it's going to be taught, whether it's here or another room. But I'll schedule that once I have a room figured out. Okay, so occasionally we might have to do one of these makeup classes. Earlier it used to be the snow causes a cancellation, so we are one class behind, so I have to do a makeup class because of snow closure. But so far that has not happened this time. All right. Okay, so let's get started. We were talking about remote procedure calls last time, okay, and distributed communication more broadly. I spoke about how you can use this concept of a network socket for 2 processes to communicate with one another. And then I also showed you some examples where you can use this concept of a remote procedure call, or an RPC, where one process can essentially call a function that resides on another process, on another machine. Rather than making a local function call, you make a remote function call, and hence it's called a remote procedure. So we'll continue from that point on, and today I'll talk a little bit about alternate RPC models, what kind of semantics you get. I will talk about remote method invocation, or RMI, which is RPCs in the Java world. Okay, for your lab, you're either going to use Python or Java. Okay, and you have to either choose RPCs or RMIs depending on the language that you are going to choose. So it's good to understand how RPCs work in the Java world. There is many similarities, so it's not very different. And towards the end, I'll talk about RPC implementation and examples. Okay, so let's get started. There are a couple slides I needed to finish from last class, which I'm going to go through first, and that had to do with when you implement RPC systems, what happens if there are failures. Okay, failures can occur in different forms. The client can crash, the server can crash, the network can drop your packet and not deliver it. Okay, so if you're making an RPC call and any of these failures occur, you have to make sure that you understand how to recover from them, or the system has to address them in some reasonable way. Okay, so there are many scenarios. I talked about a couple of them already. So if the client cannot locate the server is not running, or the server has crashed, okay, the RPC just returns an error, because there's nothing you can do. You cannot invoke the server. Okay, now you can have the network causing problems. So if the request the initial request never reached the server, nothing has happened. The server has not executed the call. So you can just have a timeout. If you haven't heard back from the server and the timeout expires, you just resend the request. Okay. Now I will say one thing. This problem of lost request messages is only going to occur if your RPC system runs on the UDP protocol. Okay, because you can run the RPC system on a TCP/IP stack, or you can run it on a UDP/IP stack. If you run it on a TCP/IP stack, this problem will not occur, okay? Because that will be handled at the TCP layer. The RPC system does not have to deal with it. If a packet gets lost, TCP will figure out the packet is lost and retransmit for you. So the RPC client does not have to retransmit, because the TCP is going to take care of that for you. Okay? So by default, okay, these days RPC system run on TCP/IP, so you don't have that problem. Okay? Neither will the reply get lost, but you can configure it to run on UDP, and the older RPC systems still run on UDP. And UDP does not have built-in retransmission in it. Okay? So if a UDP packet gets lost, the application has to deal with it. If a TCP packet gets lost, the TCP deals with it. The application does not have to worry. Okay? So this issue of lost request messages and having timeouts only occurs when your RPC system is running on something like a UDP protocol. Okay? Same with the reply. Okay? If the reply gets lost by the network, again, if it's TCP, you don't need to worry about it. The TCP at the server will retransmit, so you will actually get the reply eventually. Okay? But if you're running on UDP, then your response is lost. You time out. You have to retransmit the request, which means the server will execute it again, okay, and send back a response. And if the RPC call actually changes any state at the server and you execute the same request twice, that is going to cause problems. I gave the banking example last time, right? So you're trying to, let's say, add some $10 to a bank account. If you do this twice, then you are going to get an incorrect result, because you're doing it twice because of a lost network packet, not because you intended to do it twice. Okay, in this case, you need to make the operation idempotent, which means that you want to make sure that the server does not execute the same request twice. Okay? The way this is typically done, I'll talk about that a little bit later, is you assign a unique ID to every RPC call. You keep track of which RPC requests have been executed, and you keep the response cached. So if the same request comes again because of a lost reply, you will see that it was already executed. You know the answer. You just take it from the cache and send it back. You don't execute it again. Okay, that's what you're going to do. Okay, so you use sequence number and mark retransmission. Okay, so that's lost replies. You can have server failures. Okay, your question is? Yes. Okay, question is there any reason why you cannot present an HTTP interface between the client and the server? So if you use HTTP interfaces, you are using what is called REST interfaces or web interfaces, right? RPCs are a different method altogether, right? RPCs basically work as if you're making function calls in programs. They're not using HTTP necessarily. You can also have RPC running or HTTP. That's a different problem. We'll not look at that right now. Okay? So this is just trying to have one method of communication, which is, so we saw socket, that's the lowest level. RPC is a little bit higher level. You can also use HTTP to communicate using HTTP and RESTful interfaces. That is yet another higher level. Okay? So in the lab, you will do all of those things. Okay? So the first lab, you will do socket and RPCs. The next lab, you will do the same thing with HTTP. So you will see the difference. Okay? They're just different methods. Okay? They're all going to allow you for the client and server to talk to one another. Okay? Server failures. So this question about server failure is the server has failed. So what do you do? Okay, so maybe when the server restarts, you re-execute the message. But then the client needs to know when a response comes back, what is the guarantee that the server gives in terms of what has happened. And that's in terms of server semantics. So you have what is called at least once semantics, which means if you get a reply from the server may have executed that call at least once, maybe more than once. Okay? Maybe it executed, it failed. The server crashed and it recovered and it re-executed it. A reply came back after the second execution. That's called at least one semantics. Okay? at most one semantic says that your server is going to try at most once to execute your call, and you will get a reply if it executes once. If it executes 0 times, you will not get a reply at all. Okay, so you may have no guarantee. The server does not give you any guarantee. You send a request, nothing may come back. Okay, at least one and at most ones tell you what the server is likely to do. Okay, the best one is what is called exactly once, which means that regardless of whether there's a server failure, no server failure, if you get back a response from the server is guaranteeing you that the call was executed exactly once. And so that's the best thing. So you don't need to worry about did it execute it twice, is it idempotent? None of that needs to be worried about. Okay. You have a question? Yes.
So if the load balancer fails, is it also considered a server failure?
Your question is the load balancer failed. Is that a server failure? That is a form of a server failure. Yes. Okay. So load balancer typically used in web applications. For RPCs, you may not use it. It's directly communicating between the client and the server. But any component the server can fail. Okay? That means the server did not send a reply. Yes, you have another question. Okay, so question is for sockets, for RPCs, HTTP, how does it work in terms of latency? Where do you want to use it, and so on? Okay. So each higher level of abstraction gives, from a programmer standpoint, a interface that is more familiar. Maybe it's higher you go, the less code you might have to write. Okay. Between RPCs and REST, I don't think there's a huge amount of difference, but there's definitely a difference between socket communication and RPC communication, because RPCs require you to write less code. Having said that, the lower you program, the more efficient you can be. Right? So at socket level, there's no extra baggage of any sort. You send what you want, you get receive what you want. It will be more efficient. RPCs might incur a little bit overhead. HTTP certainly adds HTTP processing overhead, which is avoided by all of this. Right? So the higher up you go, the more layers of software you have to go through. So there is going to be higher overhead. May not be high enough that it actually matters, but if you really care about performance, you have to code at a lower level because it gives you a lot more control of what you said. Okay? But also more work, more programming complexity. Yes. Okay. What is the difference between exactly once semantics and making the operation idempotent? So making the operation idempotent simply means that no matter how many times you execute it, you get the same end result. Okay? Idempotency does not require that you have to implement the exactly one semantics. Okay? Exactly one semantics will automatically give you idempotency because you are not executing it more than one, regardless of the failure. But there are ways to do idempotency where you can actually call the function multiple times, it executes multiple times, but the end result is always the same. So you can get idempotency without exactly once, but exactly once always gives you idempotency. The question is, when you use unique IDs for requests, is that exactly once? Yes, that's exactly once and idempotent, both at the same time. Okay. All right. Let's continue. There are more things here. So you can also have the client failing. Okay, we talked about every component failing. So what happens if the client itself fails? So this is a scenario where client makes an RPC request, and let's say it's a long-running RPC call. Doesn't mean the calls have to be small. It could be a long computation. You started the server. Before the response comes back, client crashed. Okay. Now what should happen? Okay. So again, there is lots of different scenarios here. Okay. So the easiest one is what is called extermination. Extermination says if the client fails, the server can figure out the client has failed. It can then terminate the RPC computation because there is no one to send a response to. Right? So why continue when even if you got the RPC response, the client is gone. It's just crashed. Okay? So that simple thing is called extermination. You create a log, and then you check whether the client is working, or if not, you terminate it. Okay? Now, reincarnation essentially says that that's a way of also figuring out which clients have failed for long-running RPC components and so on. So rather than continuously checking whether the client is up while you're executing the RPCs, you divide times into what are called epochs. These are periods. Okay? At the end of each epoch, you say, okay, which RPCs are still running from the previous epoch? They haven't finished. And then for only those RPCs, you say, is the client still functioning? Has it crashed? If it has crashed, you terminate the RPC. The client is functioning, you continue executing it in the next epoch. Okay? So you will essentially delete computations from the old epochs for clients that have failed, and then otherwise you continue. That's called reincarnation. Gentle reincarnation is a variant of this. Is even if the client has failed, the previous client, maybe it rebooted, the machine rebooted, and there is a new version of the client somewhere else. Can we try to track it down and send the response to that client? Okay? So you delete the old owner and try to find the new version of the client process and send the response to that client process. Okay? All different ways of dealing with client failures. The last one is the simplest one, which says, let's essentially attach an expiration time to the RPC. RPC request comes, the server says, I'm going to execute it for some time t, let's say 5 seconds. Okay? At the end of that time t, it checks with the client. Okay, your RPC hasn't finished. Should I continue execution? If the client says yes, then you basically extend that computation for another time t and continue execution until a response is received. Okay? And if at the end of expiration time the client doesn't respond, then you can just terminate. Okay? All different ways of dealing with client failures. Okay? We'll come back to all of this when we do fault tolerance much later on in the course. This is just a very quick glimpse of how to make sure your RPC system is robust to all kinds of failures that can occur. Okay? Network failures, client failures, server failures, and so on. Okay? I'm going to talk very quickly about one system that originally designed this RPC. It's called Sun RPC. That's the standard RPC that you find on Linux and Mac. At least Windows has its own version of RPC. So what was called Sun RPC is now basically the standard on all Unix machines. Okay? So this is what the most widely used RPC system. But just as a by way of history, the way this system was developed was, and in those days, the company Sun Microsystem, it doesn't exist today. It's now owned by Oracle. They were designing a distributed file system called NFS, Network File System. They needed a way for NFS client machines to talk to the server machine. Okay? So they said, rather than doing this low-level socket communication, why not have the client directly call functions on the server and then execute the service? The function could be read a file, write a file, open a file, whatever the client wants to do on the server. Let's just send them as function calls and execute them as a server. Okay? And that idea basically evolved into a remote procedure call. Okay? And after they designed NFS, they said this is a general idea, so let's just make it a tool so others can use it to write other types of applications. And then that basically resulted in the first RPC tool that allowed anyone to use this idea to write a client-server application. Okay? Originally, all of that RPC ran on UDP because these were all local area networks. There weren't too many packet losses, but that meant that the application had to deal with all of the failures I was talking about. Okay? Later on, they switched the default to TCP, which is still the case today. So you don't really need to worry about network problems, network packets getting lost, because the TCP layer will take care of it for you. But you still need to worry about the client and the server failing. What do you do in that case? Okay? So we talked about that. So this is also the system that designed marshalling and demarshalling of arguments concept, where they said this is how we send large data structures as arguments to remote procedure calls. They came up with this notion of external data representation, also called XDR. Okay, so this was designed to deal with hardware, the differences between the client and the server. So you could send up any piece of data like an integer or floating point number or a data structure. You could then interpret at the other end accurately, even though there could be hardware differences. You can have little Indian architectures on one machine and big Indian on other machines, and still everything just worked well. Okay, so XDR was designed as part of the system and so on. And this system did not do much. They only said we will do at least one semantics. To get back a response, you should assume that the code executed at least. That's kind of obvious, because if you get a response, you must have executed it at least once. So it didn't say it was idempotent or anything like that. So it didn't guarantee anything. Okay? So that's just a very quick historical case study. Yeah, today there are lots of other RPC systems. We'll look at several of them a bit later in the class. Okay. All right. So let me now switch gears and talk about some alternative types of RPC systems, alternative modes by which you can have RPC calls before we jump into RMIs and the Java one. Okay. So we looked at standard RPC. It looks like a function call. Okay. You call a function, it's a remote procedure, okay, and you wait. Function executes on the other machine, a response is sent, and then you continue execution. Okay, that's the standard RPC. Now you could say, what if the client and the server were executing on the same machine? You might just have a client process is running on the same machine as the server process. They just choose to communicate using RPCs, okay, which is fine. You could do that. But now, should you have to pay the price of making a packet, sending it, try to send it over the network, but it really doesn't go over the network. It goes down the protocol stack, and the protocol says, oh, this is the same machine. It comes back up, and you give it to the person. So you put a lot of extra protocol processing overhead that could have been easily avoided. You only pay that if you want to actually send that RPC request over a network to another machine. Okay? So how can you optimize this and reduce that overhead? So that's what gets us into this notion of lightweight RPCs. Okay? So lightweight RPC is a special case of RPC that's only used when the client and the server run on the same machine. Okay? That's not a common case, by the way. Common case is the client and the server run on different machines. But if you just happen to have a client that runs on the same machine, how can we reduce the overhead? Okay? So what we are going to do is to say, let's not bother about sending the packet as a TCP/IP packet in this case. Let's just use a shared memory buffer. Okay? You have a call that you want to make it's remote. The remote is just another process on this machine, not some other process on some other machine. Let us just put all the arguments into a memory region and tell the other process saying, that's the call I would like to invoke. So just take the name of the method, the arguments, execute it, and send back the results to a memory region. So you are using a shared memory region to pass information back instead of using network messages to send back. Okay? And clearly reading and writing to a memory region, okay, has to be much faster than trying to send a packet that is going to incur TCP/IP processing overhead. Okay? So this is going to give you an efficiency, performance efficiency advantage. But beyond that, it's the same thing. It's still doing remote procedure. Okay? So that's what is the notion of a remote procedure call. There's a picture here, which I won't go into a lot of details. But by and large, what is going to happen is the RPC runtime system will figure out that the server and the client are on the same machine, and it will start using this lightweight RPC path instead of sending the normal RPC request over the TCP/IP stack. So essentially, what you will do is there are some details here. You'll push the arguments onto the stack, just as you do when you call local procedures. Okay? You will trap to the operating system kernel. The kernel will take a memory region, that's the stack, and map it into the other process's address space. But normally you cannot share memory, right? Your memory is process memory is isolated. You can't just allocate or not allocate, allow some other process to access it. So you need to make that memory region shareable. It's called shared memory. So you will do that. You will then execute the process. You will trap into the other, the server process executes, takes the arguments as if they are on the stack, executes them, sends back the return value the same. Okay? So the main concept here is you have to create a shared memory region. Okay? And then you send arguments and get the return value through that shared. Yes, question. Yes. Yes, good question. So question is, like last time I talked about unstructured communication where we are using memory regions to pass information back and forth. Is this unstructured communication? Okay? To some degree, it's a hybrid because you're still using RPCs, which are structured from our perspective. But the RPC implementation uses an unstructured method for the client and server to communicate. So from a programmer's perspective, it's structured because you use RPC. From an implementation perspective, the RPC is simply using a memory region. So that's using an unstructured method as opposed to message passing. Okay, so it's a little bit of both, depends on which perspective you're looking at. Okay, so this is a lightweight RPC was called Doors and Solaris, and what they did was they just allowed the same code. You didn't have to write different code. You just wrote the same RPC code, and there was just a runtime configuration parameter that said which library to use. Should I use the lightweight RPC library or the normal RPC library? And then it would execute accordingly. Okay, so you didn't have to change anything. It was just something you did at runtime. Okay, yes, question there. Okay, question is this somewhat like memory mapped IO in an internal device? In a memory mapped IO, a hardware device can directly write to a memory region in the OS, right? As opposed to using the CPU path, you can directly write to this. That is somewhat similar, but not really what we are talking about here. Here you take a memory page and you can essentially share that page across two different processes, and both of them can read or write. Okay, that's what it means, really, a shared memory region. Yes.
How does the client know?
Okay, question is if there is transparency, how does the client know if it's on the server? So in this case, it's not transparent, right? Otherwise, you would not know. You would just use the normal path and just do standard RPC. If you knew that, then you would use this optimization, right? Okay, anything else? Okay, so this is lightweight RPCs, but let me talk now about other RPC models you could use. I'm going to show you some pictures that explain all of these concepts. So we look at 3 or 4 different ideas. One is called asynchronous RPC. This is also referred to as non-blocking RPC, and I'll explain that in a picture. Okay? There's another one called deferred synchronous RPC that uses 2 asynchronous RPC, one in each direction. There's something called one-way RPC. In one way, so this is also a non-blocking RPC, but has a slightly different semantics from asynchronous RPC, and we'll talk about multicast RPC as well. Okay, so the way all of these differ from standard RPC is blocking. When a client makes a remote procedure calls, that client process will wait until a response is received. That's called a blocking call. Okay, that's the same semantics as when you make a local function call. The caller is going to wait for the callee to return. Okay, now you can make this a non-blocking RPC system where you can make a request of the server and the client can continue execution. It doesn't block and wait for the reply. It just continues execution. A reply comes back later and you are notified a reply is. That's called asynchronous RPC. Okay, so that's asynchronous RPC. In one-way RPC, you make a request to the server. You don't even wait to see if the server has received the request. You can just send the RPC request and continue execution. In asynchronous RPC, you at least wait to make sure the server received the request and ACK came back from the server, but then you continue execution. You don't wait for the processing. So it depends. The two differ in how long you wait before you continue execution. In one case, you wait until the server has received your request, but hasn't yet sent back the response. In another case, you don't even wait for that. You just make the call and you continue execution. Okay? So let's see some pictures that explain how this works. So here is our standard RPC. This is the blocking one. Okay. Again, x-axis is time. Solid lines means executing. Dotted lines means not executing. So you make the client is at the top. The server is at the bottom. Client makes a call that sends a request. And then you see the dotted line that says client waits for the reply. Okay, the server is going to process the reply, send back a response. Client continues execution. Standard RPC. I showed this picture last time. Right? Here is essentially our the other thing which uses asynchronous RPCs, and there are 2 of these here. Okay, so what you see here is the client has made a request, okay, and then essentially you wait for the server to have accepted that request. So you get an acknowledgement saying server received the call, server hasn't processed it, and then the client continues execution. Okay, and so then the server executes, and there's a callback. Okay, the first picture did not show the callback. So this is essentially the callback saying a response has been received. You get a notification while you're executing something else saying that response to that previous RPC has come in. And then you've got to process it. Okay. This is essentially asynchronous RPC. Any question on this? Yes.
Asynchronous RPC could be a classic for concurrency because there is a shared memory.
and both of these processes would be accessible at maybe at the same time. So in this case, if there is a deadlock, how do we resolve it?
Okay, so first thing is RPCs by default have no shared memory because the client and the server are running on different machine. Only in the lightweight RPC case is there actually a shared memory region. Okay? This is the general case we are talking about, not lightweight RPC. The lightweight RPC question, you always have concurrency issues. If you don't put a lock on your shared memory region, you are going to override something. So you always have to protect anything that's shared with a lock. That's a simple answer to that question. But that question is not related to the broad issue of, okay, because I'm sending this over the network. There is no shared memory. Okay, so RPC requests go over a network. So we don't have the deadlock case because of what you just mentioned. Okay. Is that clear? What these things do? Okay, so two more pictures, then we are done with the pictures here. So here is deferred synchronous RPC. So what happens in this case? The client makes a request, you get an ACK, and you continue execution. The server is going to execute that request, but instead of sending the reply as a callback, okay, which we saw in the previous case, the reply goes as a RPC in the reverse direction. Okay, so there are two RPCs, one that goes from the client to the server continues execution, and then there's another RPC which is essentially sending the reply as an RPC itself, rather the reply is embedded in the RPC call. Okay, so there are two messages, two invocations, one in from the client to the server, the other going from the server back to the client. Okay, that is called deferred synchronous RPC. Or it uses two asynchronous RPC to make it look like there is a somewhat like a synchronous RPC. Okay, the last one here is what is called multicast RPC. Okay, here the client makes a request. Okay, the request goes to multiple servers that are replicas of one another. All the servers will then execute that request. The client is blocked. The replies come back to you. Okay, so this is good when you are sending something to a set of replicated servers. You haven't gotten to replication or anything like that yet. But if you're a set of replicated server, you want to make that request to all of them, you can use multicast RPC. Instead of making n individual RPCs, you send one RPC, it goes to all of them. Okay, and they all execute the same thing. No question is.
So such a case, the multicast RPC case, what if there's a time difference between the response from two servers? So during that time difference, is the client still waiting or does it start processing because it has received response from one?
Yeah, question is what if there is a time difference between the two servers? Will you be blocked or not? So in this case, there is no assumption that all the replies have to come back at the same time. Servers will execute at different speeds. The replies will all come back at slightly different times. You wait until all the replies have been received. Okay, and you will see that if you look at this carefully, I don't know if you can see it from there, the two arrows from the two servers, they come in at slightly different time. The client is blocked until the second reply is received. Okay.
So what if there's a packet transmission failure towards one server? So will the right method be to send it to all again or send it to just one of that server?
Okay. Question is what happens if one of the packets to the servers get lost? So this we'll come back to our multicast and how to do them reliably. Okay, so just as you can do TCP that does retransmissions for you, there are network multicast protocols that will retransmit if some server has not received it. So you don't need to do that, handle that at the RPC layer. Okay, that's one answer. The other answer is if you don't use that, then you have to deal with that at the RPC layer, which means that you have to wait for an ACK from each server to make sure the call was received. If not, you will have to retransmit and do all kinds of extra work. Okay, you had a question? Yes.
I have listed, but how does a normal call become more RPC?
How does a normal call become an RPC call? Okay, so that's what we had covered last time. So essentially, when you write the code, you have to declare which functions are local, which functions are remote, and then the client simply makes a function call. Okay, and that comes to the RPC library, and it's going to say if it's a local call, you just call the function. It's in the same code. But if it's a remote call, then it's going to say I need to construct a message and send it over to the server. The server will execute. Okay, so just look at that concept. We've covered that also last time, but that's the basic idea. It's not very complicated. So you are going to have to decide whether each function call you make is local or remote. If it's remote, the RPC system will send a message out. Okay? And we'll revisit that when we look at RMIs. It's going to do the same thing. Just in a couple slides. Yes, question there. What's the difference between asynchronous RPCs and deferred synchronous RPCs? In deferred synchronous RPCs, in asynchronous RPC, if you go back one slide, you will see that the response from the server is going to come back as a callback, which means that the server is executing. You get a notification saying your response came back, and then you take that response and do something with it. In deferred synchronous RPC, the responses come to you back as an RPC request. The client will get an RPC call from the server, and then it will look at the RPC call and the response will be embedded. So it's just two different ways of returning the result back to the client. Okay. Any other questions here? All right. So that's multicast RPC. We are done with that. Let's talk now about remote method invocations, or RMIs. Okay. So these are just RPCs in an object-oriented world. This is how Java, as an example, would implement RPCs. Okay. So again, it's the same concept. Okay, you know how to write a standard Java program. Let's say you have classes in your program. Classes encapsulate methods, they encapsulate data. When you execute the program, okay, the classes become objects. Right? So now we have the same concepts where you can invoke a method on an object. Okay? If so happens that the object resides in the same process, it's just a standard call. You just invoke the method on that object that's already in that process. Okay? But in this case, you can invoke methods on objects that sit in other processes on other machines. Okay? So process A can invoke, let's say, object.foo. Okay? And this object is now on some other machine. Okay? So now the code for that object is not in this process. So you have to do the same thing you did in an RPC case. You will have to say this method foo and this object is somewhere else. Let's send a message to that process saying this process wants to execute foo on this method. Here are the arguments. Everything goes over the network. You execute it. Response comes back. Okay? So that's essentially the same idea. Now you are applying that to objects rather than specific processes. But some methods and some objects are local. Some objects are remote. So the method's invocation is also remote. This is why it's called remote method invocation. Okay? So we will talk more about this. So here's the picture, which looks very similar to the one I showed last time for RPCs. This is essentially the same picture in the object-oriented world. So you have the server in one box, you have the client in another box, you have the client process. It's going to invoke, in this case, a method on an object. That object is essentially that gray box that is shown on the server. Okay? And then it has a bunch of methods. So once you do this, you are going to essentially come to the stub. Remember, the stub code is auto-generated code that is going to construct the message and send it over the network. Because as a programmer, you simply call functions or you call methods. You don't actually deal with any other networking. The system is going to deal with that for you. And the part of the code that is in the system that does it is called stub code in the RPC world. In an object-oriented world or Java world, it's called proxy. Client stub is called a proxy. The server stub is called a skeleton. Okay? Same thing, just different names. Okay? And so this is the part of the code that deals with all the networking for you. Okay? So the method call is going to go to the proxy. It's going to construct a message. It's going to send that over the network. Comes to the server stub. The server stub looks at it and says, okay, it needs to invoke this method. It's actually going to call that method, execute it, get a response, construct another message that goes back, and so on. Okay? Same concept. Okay? Slightly different terminology. Okay, so we have already talked about marshalling and demarshalling of arguments. Okay, that has to happen even in a Java world because there's no assumption that Java code is going to run on homogeneous architecture. In fact, Java is designed to be cross-platform. It runs on any platform that runs a JVM. You can run Java code. That means that you also have to ensure hardware independence and all of that. So you will do the same thing we did in the RPC case that we discussed last time. You have to package all of the arguments in a way that can be interpreted on any type of machine, any OS, any hardware platform. You have to interpret it. And you will use what is called marshalling and demarshalling of arguments. But in the Java world, that's called serialization. Okay? Serialization is used in Java for many different scenarios. You can take an object, you can serialize it and put it on disk, and then you can read it back and reconstruct it, and deserialize it to get it back. You can use the same idea to send data structures over a network. You can serialize some data, send it over the network, you deserialize it at the other end, and you get it back. Okay? That automatically deals with hardware dependencies for you, because that's the serialization framework in Java already handles it for you. Okay? So we'll just use that to send arguments, okay, instead of doing anything more than this. Okay? So essentially, the client side is going to serialize, send it with all the data with the message. The server side is going to deserialize, get the parameters back. Okay, so essentially, that's the main concept. We'll talk a little bit about details here. One of the details is, how does the client know where the other object is, where the remote object is? Okay, because we didn't really talk about what you need to tell the system about this object. So there are two ways to do this. One is, in either way, you have to essentially bind to that object, which means you have to somehow locate that object. Okay? The binding can be implicit or explicit. Okay? So here, essentially, what you have is this notion of an object that you have in the system. And on the client side, you're going to have a reference to that object. Okay? It's like a pointer to the object. When you try to refer to it, somehow you will bind to it, because you'll have to track it down and say, this is where the object is. Okay? So essentially, if you just invoke the object dot some method on it without giving any extra information, that is called implicit binding. The system will have to figure out that, okay, it needs to track the object down and try to bind to it. Okay? On the other hand, you can essentially give extra information and call what the bind method. Okay? If you use the bind method, you're doing explicit binding. In this case, you can actually say this is the IP address where the process is, and extra information as part of the bind, and the server can then track it down. No, sorry, the client can then track it down. Okay? So binding can be explicit or implicit. In either case, what we are really trying to do is to figure out where is this object and where is that process, which machine is it running on, what port number is it listening on, things of this sort. That way, the client and server can communicate. For the programmer, you have said, I'm not going to tell you anything. I'm just going to call functions or methods or objects, and then, or rather, methods on objects, and let the system figure this out. But the system has to have some way to do that. Okay? So last time we also talked about using a directory service, where when the server starts executing, it registers itself with that service. Okay? So the client can always go back to such a service and say, is there a server that is providing this type of service anywhere on the network? And then you will say, yes, here is its IP address, here's the port number. That's how you communicate with the server. Okay? So that's another way you can track down where is this process or an object. Okay? So various different techniques to do this. Okay? So any of them will work depending on the RMI system. Okay? Now there is another detail here that I wanted to mention, which is how you pass parameters, okay, between the client and the server. Last time when I talked about RPCs, I said you cannot pass pointers as parameters. Okay? That's prohibited in RPC systems, because if you dereference a pointer on a strange machine, you cannot actually access the memory on the sending machine, because that's a different machine. Okay? You have no access to some other machine's memory. So as a result, RPC system will completely prohibit pointers. Okay? Now in the Java world, first of all, there are no pointers in Java. You have them only in C, C++, and so on. Okay, so there's no question of actually passing pointers, because they don't exist. But having said that, there is something called passing objects by reference and objects by value. And Java actually supports both, even in the RMI case. Okay? So if you are passing a local object as a parameter to a remote method, okay, you will pass it by value. You will take that entire object, make a copy of it, send it over the network, okay? And at the other end, you will make a copy of that object. So you now have made a copy, it's a replica at the other end, and then you will do whatever you need with the object. Okay? So if you have a method foo and you pass an object O into it, and that's a local object, you are going to pass it by value. You are going to make a copy and send it. Okay? But you may have a pointer to a remote object, which you pass as a parameter. Okay? So in this case, you cannot use copy because the object itself is on some other machine. You just have a reference to that object. Okay? In this case, Java allows you to send that object by reference. And when it dereferences at the other end, it will go back to that original object. Okay? So that is what is shown in this picture. Okay? So there are three machines. There's machine A, there's machine B, and there's machine C. Okay? So this machine A has a local object O1. Okay? Now, if you make a call that goes to this other machine, or RMI call to the other machine, and you pass O1 as a parameter to that call, okay, that entire object is sent by value. So you see a copy of it has appeared on this, okay, because that's just passed by value. Okay? But on the other hand, okay, if there is another object O2 that's here that this machine has reference to, and you pass O2 as an argument to a RMI, there's no way to make a copy because you don't have it, right? Because that object itself resides somewhere else. So in this case, you essentially pass a reference to that object through the RMI call, and then here you have that reference back, so you can refer to. Okay? So you can do pass by reference for objects only in Java. There is no passing pointers in RPCs at all. You cannot do pass by reference, only pass by value. In Java, you relax that as far as remote objects are concerned. Local objects, you never pass by reference, you only pass by value. Okay? So it's a little different in how Java deals with passing parameters than RPC world. Okay? Still, no global variables. You don't use pass global or use global variables in any methods because global variable on one machine is not accessible on another machine. So all that you should avoid. Okay? So you should only pass by value as much as possible. Okay? Other than that restriction, everything else looks like you're writing just normal code that you can just call a method on an object and so on. Okay? Any questions here? All right. So what I will do now is, yes, your question. Okay. Question is, if you pass a pointer, will that cause a security issue? There is no security issue because you can't read some other server's memory. That concept doesn't exist. And I can tell you, go read memory 10 on my machine. How are you going to read it? There is no interface on another machine saying, tell me what is on memory address 10. You can't do that, right? The OS will not let you just send a request saying, send me whatever is at this address and the memory and send you that. That is, of course, a security issue, but there is no, it's not allowed. Right? So you cannot, the more technical way of saying it is you cannot dereference a pointer on another machine. You can only dereference pointers on your machine. And furthermore, when you dereference the pointer, that memory address has to belong to that process. You can't go and look at some other process's memory. Even that is not allowed on a local machine. Right? So whatever you dereference is only your address. You cannot even see some other process's address. And clearly you cannot go to some other machine and see some random process's address. So none of that is allowed by the OS as it is. So you can't, I mean, you can pass a pointer, but it's meaningless. When you try to dereference it on the other end, it will try to look at that address on that machine's memory because it just looks like an address. It's an integer. That address is just an integer saying address number 100. And that's memory address 100 on that machine. So on other machine, it doesn't make any sense. It's meaningless to dereference. Okay, yes, question.
So in Java perspective, so by default, all the calls, whatever happens, if it's local, it's usually passed by reference. Now in this case, RPC, they're actually passing it by value. They're copying the object into another object and passing the value.
Yes.
So does it mean that these objects, whatever we pass, should be strictly read-only objects? Or does it mean that in this particular case, it is still passed by value, but it still gives the user the feeling that it is passed by value?
No. So question, I don't fully understand the question, but you are saying that when you pass an object by value in an RMI case, should it be a read-only object or something? They are asking. So there is no requirement what the object should be. You are going to pass it by value. You can change the object on the other end, just not going to change on the actual sender, right? So here is an example we just showed. Here's the object O1. The machine A made an RMI call to machine B, or in this case actually machine C, and it passed O1 as a parameter. Okay? That object went as passed by value. and we have a copy of it here. So the same method, same data, there's a copy here. Now this machine can invoke methods on this object. It can change the data in that object. All that is allowed. It's not going to reflect on the other end. That's what pass by value does. You can change the pass by value parameter in the function. It doesn't change the original value. So same thing is going to happen. It's not going to change anything at the other end. And that's what you need to understand. Right? If you did pass by reference, anything you change is actually changing the original parameter. Here you don't get that. That's the only difference here.
So if I call a normal function and if I call a RPC function, does the user actually know that these two would be different functions, or it is hidden from the user?
The question is, does the user know? So the programmer is writing this code, right? As a developer, you say, I'm going to make an RMI call. So you know exactly what you're calling. So it's not like, only thing is, it just looks like you're calling methods. So you're using the same way of programming. You just call remote methods the same as you call local methods, but you better know that it's a remote method, because you need to know where the code resides if you have to bind and so on. So it's not hidden from you as the programmer. User doesn't care. User is the one who's running the code, but they don't need to know what the code is. But programmers are the ones writing the code. So they will know whether you're making a remote method call, you're writing that code for a reason, right? So it's not hidden from the programmer. Yes, this question.
What object is passed by reference statement? How does machine C find where that object also open if a connection?
Yeah, that's a good question. The question is, when you pass an object, how does the machine C will, by reference, how will the machine C know how to get to that object? Okay? So when you're passing this object, you have a special type of object. It's called Unicast remote objects, right? So those remote objects are a special type of objects in Java, and Java supports what is called a system-wide reference, which means that I can dereference that object on a machine, and it keeps track of where the object resides. So when you pass this object by reference, that whatever you're passing contains information of where the object resides, so I can dereference it. So it may include information of the IP address of the machine that the object lives and all of those other things. Okay? Otherwise, you can't figure this out. Right? Yeah, the question is, would machine C make a connection to machine B and make another call? The programmer would just call o2.foo, like a method. The RMI system in Java will then open a connection and send a message to invoke, just as you call any other RMI method. Right? The short answer is yes, you have to make a connection, but the programmer does not do that. That's the more important part. You just call methods on objects. That's all you do, as you did for anything else in Java. Okay, something else, yes. The question is, does RPC exist because faster than HTTP? RPCs have been around since the 1970s. HTTP was invented in 1995 or 1993. Okay, so RPCs predate HTTP by more than 30-40 years. Okay, that was the standard way to write distributed applications other than socket programming. So before HTTP existed, only two ways you write a client-server application: you either use the sockets or you write using RPCs. Okay, once HTTP was invented, you had a third way. Okay, so I would not say that one is faster, slower, other than HTTP protocol processing. Okay, there are web applications that use HTTP. Not every application has to use HTTP to communicate. There are plenty of applications that don't use HTTP at all. They use standard RPCs, and we'll see some of that as well. Okay, and you will write some of this, so you will understand the differences. So RPCs go way back, well beyond HTTP was even invented. So it's a much more established, older way of communication between clients and servers. Yes. Why would you continue to use RPCs because instead of HTTPS? HTTPS has web processing overhead that not every application needs. Right? HTTP is not the only way to write client-server application. In fact, it's only used if you're using web technology. There are all kinds of applications that don't use HTTP. Like let's say you are trying to print a job on a network printer. Okay? You don't need to send your file over HTTP. You can just make a RPC request, send the file, and print it. So you same thing. You want to make a connection to a remote database. You don't need to use HTTP. There are all kinds of scenarios where you don't need to do it. Right? Only if you're writing web-based microservices, then you think let's use HTTP because this is going to live on the web and use web technology. So plenty of applications don't need it, right? Because they don't actually care about whether you're using HTTP or not. All right? Okay. So some snippets of code just to give you some sense of how all of this works. We'll start with Java RMI. We'll talk about RPCs. I'll talk about gRPCs, which is Google RPC. That's what you're going to use, and some more too. Okay, so let's start with Java RMI. Okay, so in Java RMI, like any RPC system, you have to at least write two components to your application, a client and a server. Okay, the server has to define an interface, okay, which is essentially all the methods it exports. That's the interface, and it has to provide an implementation of the interface, which is the code for the method. This is what the server does. So if you have to write the server for Java RMI, you have to have two pieces. You say, this is my interface. This is what I export. Okay, those are all the remote methods, and then you have to provide an implementation to this. Okay, so and then the server program is going to create the server object and register the object with the remote object registry. This is our directory service that you can go look up and say, is this server with this name running anywhere? Okay? That's what you would do in the Java code. And then the client, to connect to the server, when the user writes the code for a remote method, okay, it's going to come to the stub, and the stub is going to say, okay, here's a remote method that's being invoked. Okay, on this object is going to look up the object registry, saying, where is this object? Which machine is it running on? And then you find it, and then you make a connection, and then you basically connect to it, send a request. Okay, so essentially, there's an RMI registry which is called the server side name server. That's your remote object registry. Okay, so there's this extra piece that is running somewhere in the network that the server registers itself with. Okay, you can of course directly bind to the server with hard code, the IP address, and so on. In that case, you can't move the server. In this case, you can just run the server on any machine. It registers itself. You can track it down and connect to it. Okay, so there's a better way to do this. Here is some code. I don't know if any of this is readable, but it's in the course notes, so you can go look at it. So this is the three pieces here. That's your interface. So that's what you declare, saying this is the server. Okay, so you will say that, see that it's saying that is java.rmi.remote. So here's your hello class. Okay, so we're writing a hello class, and we say it has extends remote. So this is essentially a remote class or remote object. Okay, it has essentially one function, the remote function. It's just say hello. Okay, and so that's your declaration saying the remote method is called hello, or so not the remote method. The remote object is called hello, and it has a say hello. Okay, that's your interface. Here's the server that's actually going to implement that code. Okay, so the server essentially will first try to register yourself. So you'll say locate registry, get registry, and then you will say call the bind function saying I am a server that provides the hello service. So that's my name. So if somebody wants to look for this object, they have to say, is there a hello service running somewhere, and ask the register. So you register yourself, okay, and then essentially you're just going to sit and wait for request. Okay, and there's your client. Okay, it's going to first track down where so you do a registry.lookup saying where is the hello server running. Okay, and beyond that, you're just going to call the say hello function. Okay, and just as you call any other method, and the say hello function is going to, there's all sorts of exception handling code there you can ignore, but by and large, you're just going to call a method. Okay, like I said. So, and that's going to connect to the server and invoke the hello function. Yeah, yes, question. Will the remote object be the unique name? The service has to have a unique name, yes. If there are two hello servers running, you're in trouble. You don't know which one. That's what you do. Of course, you can't register to the registry, will say this name already exists. So you should have a unique name, yes. Okay, all right. So few different details, then we are going to get to other types of systems. So first thing is when you write any server, and you will see this, yes. Can you explain the interface code? Okay, so all right. So the interface code is essentially trying to declare to the system what are all the remote methods the server exists. So it's a declaration of all the methods. So you will say, here's the object that's remote, and you'll have a list of all the methods, and all the arguments they take and so. Okay, so the interface code is essentially used to generate the stub code, as we'll see in just a moment, because the stub code has to figure out what are the remote methods, how to construct messages for that method, and so on. So you need a compiler or the RPC or RMI tool to have something to work with that, so they can construct the right type of messages and so on. So that's a declaration that allows you to do all of that, to do the auto generation of a code. Okay, same will be true in most RPC system. You'll have a declaration that's used to do auto generation of code, and then the client code and the server code that you actually write for them to communicate. Okay, so next is a couple of additional details that you may want to keep in mind. First thing is, although I did not mention any of this here, whenever you write any server, okay, you assume that multiple clients can send requests. You don't write a server saying only one client is going to make it. If it's a web server, you can have multiple users trying to make web requests. Okay, if it's any other type of server, you should assume the same thing. Okay, so in other words, the server has to support concurrency. The server has to assume that multiple clients can send it concurrent requests and things of that sort. Okay, so whenever you have concurrency, you then want to make sure that you are essentially using synchronization at the server, because there may be shared data structures. You don't want two calls to from two different clients trying to make changes to shared data structures and so on. Okay, so all of the server code that you write for any client server application has to support concurrency. Typically, you'll do this through threads. Okay, you can also do non-threaded code, which is more advanced. We won't worry about that right now. But you will essentially have threads in servers. Whenever you have threads in servers to support concurrency, you have to ensure that any data structures that the threads access have to be protected using locks or semaphores or something like that. Okay, so you will have to write that code. Okay, but if you are doing this in Java, that some of that comes for free, because Java has built-in support for synchronization for any class. Okay, because you have something called monitors in Java, okay, so essentially can make a method synchronized, and then Java automatically puts a lock on. Okay, so if we are writing Java code, concurrency is still achieved through threads, but synchronization is much more straightforward. You can just use the synchronized call on methods, and you essentially get synchronization without doing any extra work. Okay, so it's something you may want to keep in mind if you're writing some of your lab code in Java, and you need synchronization. That is actually going to work well for you. Okay, now the only question that you want to keep in mind is when you're doing remote calls on synchronized objects, you can actually have problems, because now multiple clients are trying to grab a lock on a synchronized method over a network. If the remote method is synchronized, you make it synchronized, and you have multiple of these requests coming in, and then someone has to block, because only one method can, or one client can access the method at any time. That's what a lock will do for you. Okay, so then you have to think about, if you're designing the Java RMI system, where are you going to make these requests that are waiting on a lock or the monitor block? You can block at the server. When requests come in, the server says that method is actually already being executed by some other client. You can't execute it because it's a synchronized method, so then you will block at the server. Okay, or you can say, I can block at the client itself. The client can first check with the server, is the lock available, only then even send the request. So you can make the server, the request, block at the proxy or the client itself. Right? Now that's the second technique, is what is the default in Java. You don't actually send things to the server, because the client crashes, then you basically hold the lock and you're in trouble. So you basically block at the client end. Right? Just implementation details. You don't need to really worry about this, because it's all taken care of under the hoods for you, but something you should know. No question is. Yes. Okay, question is, if you have the blocking at the proxy or waiting for the lock, you check the server. Server said lock is available. Before you send the request, some other client comes and grabs it, right? So this is a good point you make, because you have to make the lock a distributed lock. Okay, it's not a centralized lock. We will study how to implement a distributed lock in a few lectures. Then you will see how this can be actually implemented under the. At this point, we haven't studied. We know what a centralized lock. But when you have a distributed system, the lock concept has to work across distributed applications. That requires that the lock itself actually has support for distributed system, which this normal lock would not have, because you might have the race condition you mentioned, and then you are in trouble. Two clients have entered the monitor at the same time. So it requires extra work, but we don't have that concept yet. We'll get to it at a later point. Okay. All right. So let's now look quickly at how do you do this in the RPC world. Okay. So very similar concept is going to apply if you want to write a C or a C++ program that tries to do RPCs. Okay. You will have to write three things. Okay. You will have to write a header specification file, okay, which you call a .x file. That is the interface that lists all the RPCs you are going to write in this program. Okay. So it's like a header. Think of it almost like a header file. You'll write the name of the function. You'll say that it takes these methods. So my first method is integer, second method is an array. You declare the entire, all the functions, what are the parameters, and so on. That sits in one file. Okay. And then you write the client side code and the server code. The client code and the server code do very similar things to the Java snippet. Essentially, the client code is simply going to, the server code, when it starts up, it's going to register itself with some sort of a registry. Okay. In this case, it's called an RPC registry. It's called binder. In the Java world, it's called an RMI registry. Okay. Same concept. So it will register itself. Client has to look for the server, and then you just make a function call, okay, which is a remote method. And then the function call goes over the network. So same concept is true. So you write three pieces of code: a specification file, the server procedure, that remote procedure, and the client code. And this picture is going to show you how you actually create the application. Okay. So you will use a tool called RPC Gen. That's a special type of an RPC compiler that is going to auto-generate all the extra code for you. Okay. So RPC Gen is simply going to take the specification file, which is the same as the interface file in Java. Okay. And then it's going to construct these 5 or 6 different files for you. So you see there's an XDR file that does all the marshalling, demarshalling of argument. There's a client stub code. There's a server stub code. It's auto-generated. You don't write it. Okay. All you need to do is you take your code, you take the client stub code, you compile it together, you have the client binary. Okay. On the server side, you take the server stub code, you take the server code, you compile it, you have the server binary. And now this client and the server can communicate. Okay. That's essentially how you generate the program from the original code. Okay. In the lablet that we just gave out yesterday, there's a RPC code, and you can actually compile it, and you will see that it will generate all of that file, and you can look at the file if you are interested. Okay, but mostly you should run it and make sure it works. Okay. Okay. So that is essentially the sample code in the lablet. So go and look at it. Okay. And here is essentially how you run it. Okay. So here, when the server starts up, it registers with the registry. Okay, this binder is called port mapper in Unix terminology. The client has to look up the port mapper to find the server, and then you are going to essentially communicate with the server. Concepts are very similar, both in Java and C world. Okay, so now let's talk about 2 other systems quickly that are also part of the lablet. How do you do this in Python? We talked about C, we talked about Java. How do you do all of this in Python? So Python has, as it turns out, multiple libraries that allow you to do all kinds of remote procedures, remote methods, and so on. The one that we will have you use is called Pyro, Python Remote Objects. Okay. Look very similar to Java, okay, but now you're writing all of your code in Python. I don't know if anybody can read this, but I'm going to go through very quickly the high-level code here. So that's the top part, is essentially the server code. Essentially, you are going to create a Pyro daemon. So this is the server process that's going to run. Okay, you are going to register it with the registry saying here is the hello world service. Okay, so and then you have the code for the hello world, which is essentially the get fortune is your remote method. So you are going to say call get fortune as a remote command, and he's going to just say hello, your fortune is X, and say something. So a server is basically fortune teller. You send it a request, it sends you some text that is your fortune. Okay? So essentially, that's what's going to be the server code. Here is and then you just run the server. Okay? That's essentially, you start Python, and you run that code and the server starts running. Okay. Here's your client code. Okay. So as you can see, all that the client code is saying is it's calling greeting maker. That's the name of the server, or that object rather, dot get fortune. Okay. So you just called it like you're calling an object in Python with a method. Okay. And that's all the things that I talked about is still going to happen. Okay. So you do have to register the server and so on. Okay. You had a question there? Yes. The question, how do you handle dynamic typing of the language? I think there are some restrictions on what you can do when you're calling remote objects and sending parameters and so on. You have to declare it, you have to register it, and so on. I actually don't know the details of how Pyro does it, but there are RMI systems and RPC system where you can do what is called dynamic typing. You don't even have to declare what is the object, what are the parameters. You can figure that out at runtime on the fly and send messages and things of that sort. So in a system that does not use strong typing, I think that's the best approach, because you don't know ahead of time what to expect. Okay? So this will require you to do extra work at the runtime layer to do all of that. Now, having said that, I'm not saying Pyro actually does that. This is just my intuition of how it probably does, because I actually don't know the details of how Pyro will handle that issue specifically. Okay. Yes. Okay. Question is, the daemon, does it run separately? Is it a separate process and so on? That is actually a separate process that you have to run in addition to the server process. The server process quits, that can still be running, right? So you just have to run that as a separate daemon process. Okay. All right. So one last thing before we end today, which is another RPC system, which is has taken over largely from Sun RPC system because it has a lot more flexibility. This is called gRPC. Okay, it started from Google, so G actually stands for Google, but we just call it gRPC. Now, this Google RPC system is meant to be a high performance system. Okay, so the thing that gRPC does that other RPCs don't do is it has actually language independence. Okay, RPC system, RMI system, we assume the client and the server are actually written in the same language. You have to write in Java case, both the client and server written in Java. In the RPC case, it's written in C or C++. gRPC allows the client and the server to be written in different languages. You can write the server in one language and the client in another language. They can run on different hardware and still works. Okay? So this is a more flexible system where you don't even assume that the code on the client and the server is written in the same language. It is a language independent, platform independent RPC system. Okay? So that's a good part about it. So you can use it to write code in Python, Java, C, C#, Go, Swift, Node.js. All of them actually are supported by gRPC. So you can write any client or any server in any of these languages and the server in another. Okay? Now, we were being asked about lots of HTTP questions. gRPC essentially runs on top of HTTP. Okay? It doesn't actually make HTTP requests. It's simply using HTTP as transport. Okay? So it's essentially sending RPC request over HTTP as the transport. Okay? And then it uses another concept called protobufs, which are essentially used to serialize and deserialize messages. Okay? So because we have to do marshalling and demarshalling of arguments, okay? That's not easy if the languages on the client and the server don't match. I make a call and the server is written in some other language, so you can't actually go and figure this out. So what you have to do is you have to make explicit buffers for sending information back and forth that can be recognized by the client and server, even though they're written in different languages. Okay? And this is called a protobuf. So for whatever information you pass between the client and the server, you have to declare a buffer, which is called a protobuf, and say this is the structure. And then you tell that to both client and the server, and then it doesn't matter what the language is, because I already said, this is how I'm going to communicate. Okay. So very quickly, here is a protobuf thing, and then we'll end. So you essentially have to allow message structure for communication. So you will have declared a dot proto file. A dot proto file will say here is essentially a data structure. Here's a request, a search request. A search request consists of a query, that's a string. It has a page number, that's an integer. It has a result per page, that's another integer. So you constructed this data structure as a protobuf. So that's a buffer that will have these three pieces of information. Okay. Once you declare this, then you can tell the client and the server, this is what I'm going to use for communication. And then it doesn't matter what language you write it in. So there's a protocol compiler that will use that protobuf and declare your classes. And then the classes are going to essentially use that protobuf to communicate back and forth. Okay. So the first thing in gRPC is whatever you communicate back and forth, you have to essentially declare a protobuf concept. Okay. So, and then once you have the protobuf concept, you still have to declare your RPC methods. You will have to put that also in the protobuf file. It will construct stubs, and then you can essentially use that stub depending on the language of the client and the server. Okay. The rest of the concepts are similar, but because we have language independence, some extra work has to be done that you would not do if you had assumed the same language, which is you have to have this extra thing called a protobuf that sends things back and forth. Okay. So what I will encourage you is to look carefully in the lablet of how gRPCs work. Okay. Because the lab that is going to come out today, okay, which I will have two parts. First part is you will write a client and a server using socket communication. Okay. You can use Python to do that. You can use whatever else you want to do that, but you still have to use socket. You can use Java or Python, but socket communication. Okay. The second part requires you to implement the same client and server application using gRPC. Okay. So in this case, you will essentially use gRPC, you will use protocol buffers and things of that sort, and try to write the same. Okay. Next time, which is lab 2, you will use HTTP and a web service to write the same application. But that's coming later. Right now, you just need to know, write socket code. You need to know how to write threading code. Okay. If you don't remember how to write threads code, please go look up an undergraduate textbook where you have the concurrency chapter. You need to at least know how to create threads and so on. You also need to know how to use basic synchronizers. It's not complicated, fairly straightforward client and server application, but it is a concurrent server. It has to have the ability for multiple clients to connect and make requests, and there should be no race conditions or things of that. Okay? So you need to know these concepts for you to finish lab 1, which is going to come out. But to do that, I would say look at all the sample code we gave you in the lablet, because it has all the basic scaffolding you will need for the lab. Okay? You can then use that to essentially write the code for the lab. Okay? We are here every day. If you have questions, come ask in office hours. Okay? So 7 days a week, there are office hours. Between now and end of the month, you have to finish a lablet and a lab. Okay? Add drop ends tomorrow. Last chance to figure out whether you want this course or not, but a lot of work will starting tomorrow. Okay. All right. So we'll end it here, and we'll continue next time. Okay. Thanks.